Bismillahirrahmanirrahim. Assalamu alaikum. In literature, there exists a variety of root finding methods in literature, and in our today's talk, I'll be taking start one of the method from the numerical techniques under the title of the bisection method. This is the method which helps you to locate the root of some function which are bit not very simple to find out their roots. This is basically applicable to functions of single variable. If you are given a function which is a function of single variable, then we can apply this method in order to find the root of that particular function. The procedure starts with the function. So first of all, as usual, we'll be covering the details of the method and how actually this method works, and at the end I'll be applying it in order to solve a question. So here let's take start. The title of the method is the bisection method. The other name of this method is halving the interval method, and another name of this method is generally given is named as the Bolzano's method. So these are the different heads or different names given to this method, and perhaps you will be finding some other names in the literature. So these are the most common names given to this method. If we take start from a very simple equation, say x plus 2 is equals to say 5. This is a simple linear equation of single variable. And if you are looking for the value of x, which is going to place here in order to balance the two sides, so it will be not very difficult for you to how we can locate the value and just shifting this quantity on the other side, and we can find out the value of x which is going to satisfy this equation. But if I make a change in this equation and introduce here a trigonometric function, say sine x, and now perhaps it is not very simple to say which number or which value is going to satisfy this particular equation. And further, if we change it like this, say log of x, so it makes it a bit more complicated. So there are a variety of equations in which we are looking for the root may appear like this. So here we are given a function whose root we are not able to find out by using some direct technique. So for this we use the numerical method under the title of the bisection method. So here we start the procedure. We are given a function, say f of x, and we are looking for the root of this function. So first of all, you have to define an interval in which the root of the function lies. And for the time being, I assume the root is somewhere in between a and b. And make sure there should be at the most one root in between this interval. There should be not more than one root. And this is the function whose root we are looking for. And this is the interval in which lies at the most one root. Okay. And here if I show it just by a straight line indicating the two endpoints of the interval, so this is the situation so far. And how we can say the root of this function lies within this interval? So this function for these two endpoints must satisfy a condition. And the condition is the value of the function at a, which is the left hand point, and the value of the function at the right hand point, and their product should be negative. So this is the condition which must satisfy in order to guarantee that the root is somewhere in between these 2 points. So this is the most important condition for the bisection method. Okay. Now from here, whenever we have the product of the two quantities a negative number, so definitely at the most one of them should be with the negative sign. Okay, one with the plus sign and the other should be with the negative sign. So for the time being, in order for the procedure point view, we take the value of the function at A is a positive and the value of the function at B is a negative. Okay, you can take vice versa. You can take the negative here and you can take the positive here. Both will work. And for the time being, I'm taking here the value of the function at A is positive and the value of the function at B is negative. And whenever we take the product of these two, the result will be negative. The same, excuse me, the same I show here. The value of the function at A is positive and the value of the function at B is negative. Okay. Once again, why do we fulfill this condition? Because this guarantees that the root is somewhere in between this boundary. So this is the first condition you have to satisfy. Else, might be you are taking some interval where there is no root, and then of course you are not able to find it out. So this condition must hold before taking start. After doing this, now we go for the search of the root. In order to do this, we find out the midpoint of the interval. And I label it as, say, x1. x1 is the midpoint of the interval A and B. How do we find out the midpoint? We already know the formula. If we are given the endpoints, so we take the sum of these two endpoints and divide it by 2. So this provides you the midpoint of the interval. After finding the midpoint, the next step is to find out the value of the function at x1. And whenever you find out the value of the function, this is the function, you have to place this value x1 over here, and then you will be getting some value. And that quantity or value may have three possibilities. Either this can be less than 0 or equals to 0 or greater than 0. So these three situations may occur. Either this can be negative or this can be equals to 0 or this can be positive. Okay? We consider the case whenever it is not equals to 0, because if it is equals to 0, then we are at the root and there is no way, no need to go anywhere because we are at the root which we are actually looking for. So for the time being, we assume that one of these two conditions holds. And for the time being, let's assume the function is having a negative value or negative sign of the value at x1. I repeat this step. I said whenever you find out the value of the function at x1, there can be three possibilities. Either it can be negative, positive, or equals to 0. I know the step for the case of 0 because whenever you are at 0, so we are at the root. So there is no need to go anywhere. And we here assume for the time being, for this particular situation, that the value of the function is negative. Either you can take it as positive, but whenever you are solving a question, the excuse me, the statement of the question will decide either it is positive or negative. But for the theory point view, I am taking it as negative. Okay, so here let's show it. The function is having the value which is negative. And now we have two parts of the interval. You can see in the intervals figure, you can you have two parts, one from the point A to x1 and the other one is from x1 to b. And now we have to discard half of the part out of these two. Which part we have to discard? This will be decided on the basis of the sign. And this condition we have to keep it in our mind. Whenever we select an interval for the next iteration, for the next step, so this condition must hold for any two endpoints. Okay. If I take the first interval, and the interval is from A to x1. Okay. And here you can see the sign of the function's value at A is positive, and the sign of the function's value at x1 is negative. Now you can see, if I take the product of these two, the result is negative due to having opposite sign. So this condition holds if I take these two endpoints for the next iteration or for the next calculation. And if you take this interval from x1 to b, let me show it here. Here we have a positive sign, and at b we also have the positive sign. Sorry, I have written down wrong. Here it is a negative sign, and there is also negative sign. Okay, that's fine. It's okay now. Now you can see here, if we take the product of these two, so it is not going to fulfill this condition of less than 0, because both the signs are negative, so the product will be positive. So this indicates how actually we select the interval. For the next interval, we have to fulfill this condition for the endpoint. So here you can see this part, excuse me, this part from x1 to b can be discarded from the domain, and the new domain for the next interval is from a to x1. And for the for the completion of the iteration, we'll be writing it here as the product of the function at a and the function's value at a and the function's value at b, x1, gives you the negative sign. Therefore, the root of the function, lies in the new interval, and now the new interval is from a to x1. So here you can see the interval has been squeezed and half of the interval has been dropped down. And till here, the first iteration completes. And now you proceed for the next iteration. And whenever you go for the next iteration, your new interval is this one, a to x1. Let me show it here once again. Okay, I can erase this from here. Now we go for the search of the next iteration, number 2. So here I draw here once again the interval whose left point is a and the right point is x1. And the function's value at a is negative, sorry, this was positive, and the function's value at x1 is negative. Okay. And now this is the new situation here, and we have these two situations, the values of the functions. And once again we go in search of the midpoint. This time I label this midpoint by x2. And x2 can be calculated by using the same formula, sum of the two endpoints divided by 2. So after finding the new midpoint, you will be going to find out the function's value at the new midpoint. And once again, there can be 3 possibilities. The same 3 possibilities, either the value can be negative, or it can be positive, or it can be equals to 0. So for the time being, we ignore the 0 situation. We this time take it as positive. Okay. Previously we have taken it as negative, and this time we take it as positive. But in actual, whenever you are solving the question, so this sign will be, of course, appearing after making the calculations. So here we, for the 3-point view, is taking the function's value at x2 is positive. And now once again we have to drop the half of the interval. How do we decide which part of the interval we have to keep and which we have to drop down? We have to fulfill the same situation here. If you look at this, here, if we work for this first part of the interval from a to x2, so both the function's value at the left hand point, which is a, and the right hand point at x2 having the same sign. So this is the way through which we can decide which part we have to drop down. The function's values will decide which part you have to keep and which you have to drop down. Where we have the same sign, of course, these will not work for our situation. The function's value having the opposite sign, you can see here, these two have the opposite signs, and the product of the function's value at x2 and the function's value at x1 gives you the negative sign. So this means that the new interval for the next iteration will be from x2 to x1. So here we write down as the product of the function at x2 and the product and x1 is negative, fulfilling this condition of negative sign. Therefore, the root lies in the new domain from x2 to x1. Okay, and one more important thing is you have to keep the order of the numbers. You should not write x1 first. Whichever comes first, you have to keep it as it is. So x2 is coming first and x1 is after that, so we maintain the order of these numbers. In here we have covered the second iteration, and if you go through all these steps which I have covered here, you can see each time half of the part of the domain is going to be dropped down, and remaining is the portion where actually the root of the function lies, and each time whenever you're dropping down, the interval is getting smaller and smaller, and the time will come whenever you will be almost at the root. So after knowing all these information about the bisection method, now we go to apply it on a question. The question is, we are given a function, say x cubed minus x minus 11. Okay, now the how actually we find out the domain in which the root lies. This is the important question to answer, how actually we locate the domain. And second question generally arises in the minds of the students, whenever we work on an iterative process, it is perhaps never ending process, and how we can stop it. So there can be different ways to take stop of this method. So generally, from my point of view, I take whenever two consecutive iterations gets identical for up to a specified number of decimal places, then we can take stop. So here I'll be keeping all my calculations up to 4 decimal places, and whenever we reach to a place where we have for any two consecutive iterations, same results for two consecutive iterations, then we can take stop. Okay, and in this case, the second question is how we can find the domain in which the root lies. So here we I give you the idea how actually we look at the domain. So whenever we are interested in to find out the domain, so we assign arbitrarily different values to the function. I take start from 0. If I put 0, so here you can see on the right side, I have the values minus 11, which is negative. Similarly, if I keep on putting the other values, say 1, I get here 1 cube, and minus 1 minus 11, this is equals to minus 11 again. So still you can see the sign is the same. And if I assign say x equals to 2, so here we get 2 cube minus 2 minus 11. So 8, 19 minus this one. So how much it is? Minus 5. Okay. And the sign is still same. There is no change in the sign. And next we take x equals to 3. And whenever we assign it, we get 3 cube minus 3 minus 11. So this gives you 27 minus 14. So this gives you plus 13. So here you can see we have the different signs here. And these two different signs are appearing at the two values of x which are in between 2 and 3. So this indicates thus, as the product at 2 and the 3 gives you the negative sign, therefore the root of f of x lies in between 2 and 3. So this is the simple way to locate the domain in which the root lies. Okay, after deciding the domain of the interval, I hope you can understand, you can assign different values. Sometimes you have to assign some negative values as well. The main idea is that you have to assign different values just to locate where the sign of the function's value changes. And where two consecutive values gives you the opposite sign, like here you can see we have the opposite sign. So this indicates the root is, of course, in between 2 and 3. So I take this an interval to take start of your procedure. Now we go for iteration number 1. For the iteration number 1, let me show it here. All these information we have gathered so far. A, I can take the left hand point, which was the domain in which the root lies, and B, I take it equals to 3. I call it as 2A and B. And now I go in search of the midpoint, x1. So here, whenever we are interested in to locate the midpoint, so we have to use the formula A plus B by 2. So 2 plus 3 over 2. So 5 gives you 2.5. Okay. And whenever you substitute this value into the function, we get 2.5 cube minus 2.5 minus 11. And on simplifying, we'll be having value 2.125. And you can see the sign is positive. Here we are not giving the positive or negative sign arbitrarily, but we actually are getting the positive sign after making these calculations. Okay. So here we write down x1 is 2.5 and the function's value at x1 is positive. Okay. Okay. Now we have to decide to drop one of the section from the whole interval. Here the function is having the negative value, if you remember, and here we have the positive value. So as I told you, wherever we have the same sign at the two endpoints, so we can drop down this portion. So we have the same sign here, you can see. At x1 and at b, we have the same sign of the function's value. So this section can be dropped down from the domain. And the new domain will be in between from the value of 2 and 2.5. So here we write down as the product of the function at a, which is 2, and the function's value at x1, which is 2.5, gives you the negative sign. Therefore, the root of f of x lies in between the new domain of 2 and 2.5. So here you can say half of the portion of the domain has been dropped down. So till here, this completes your first iteration. Now we go in search of the second iteration and a better root for the given function. So let me show all these informations here. The new domain is now in between a equals to 2 and x1 is equals to 2.5. Here we have the value which is negative, and here we have the value of the function which is positive. Okay. Now we go in search of the midpoint, which is x2, and x2 can be obtained now taking the sum of the two endpoints 2 and 2.5 whole divided by 2. So whenever you divide it, we get 2.25. Then similarly, we'll be finding the function's value at 2.25 whole cube and 2.25 minus 11, and on simplifying we'll be having another value minus 1.8594 up to 4 decimal places, and this is negative. Okay, you can see the sign is negative. So here I show it. This is 2.25 and the function's value at x2 is negative. So as I told you, wherever we have the same sign at the two endpoint, you can see here from a to x2 we have the same negative sign. So this section now will be dropped down from the domain, and the new domain for the next iteration will be x2 to x1. So here we write down as the product of the function at x2, which is 2.25, and the function's value at x1, which is 2.5, gives you the negative sign. Therefore, the root of the function f of x lies in the new domain. The new domain is from 2.25 and to 2.5. You have to keep the order of the number as they are appearing in the figure. So till here, this completes your second iteration. I hope after doing these two iterations, now the idea should be clear in your mind how actually you proceed. I'll be doing a few more iterations for you. Let me erase all these from here. Okay, now we go for the iteration number 3. And before taking start, we have to reconstruct the figure once again. The new interval is now from x2 to x1. So the left hand point is x2, which is equals to 2.25, and x1 is the right hand point, which is 2.5. And here we have, you can see here, we have the negative sign of the function's value, and on the right side we have the positive sign of the function's value. Okay, this figure generally makes your work a bit easier in order to understand which part we have to drop down and which we have to keep. Otherwise, there is no need, in actual, there is no need to draw all these. Now we go in search of the next midpoint. I label it, say, x3. And x3 can be obtained by taking the sum of the two endpoints plus 2.5 whole divided by 2. And whenever you divide it, you will be getting 2.375. Okay, and now you calculate the function's value at this new middle point, which is 2.375. So 2.375 whole cube, 2.375 minus 11. Okay, now you can use your calculating devices. The result is 0.0215, and here we have a positive sign. So let me show the results here. The result is 2.375 here, and the function's value at x3 gives you the positive sign. And now I hope you can understand and you can decide of yourself which part you have to keep and which you have to drop down. You have to look at the sign. If you have the same sign, you can see here we have the opposite sign here, but here we have the same sign. The same sign section will be dropped down. Opposite signs you have to keep. So here we write down once again the product of the function at x2 and the product of the function at x3 gives you the negative sign. Therefore, the root lies in the new domain of 2.25 and 2.375. Okay, after doing this third iteration, the idea should be more clear now, okay, how actually we proceed. And one more important thing you have to note down, okay, each time whenever we go for the next iteration, the value of the function you are getting is getting smaller and smaller, or approaching towards 0. And this indicates this method guarantees you to take towards the root, and you all know that whenever we are approaching towards the root or we are at the root, then on substituting the root into the function, the output should be 0. So here we will be having 0 up to 4 decimal places. Might be you have no 0 after that, but we have made all these calculations up to 4 decimal places. And here let me write down the results for this method, for this particular question. Okay, the result will be telling after almost 22 iterations. I hope this is a big lengthier process and a lot of calculations you have to do. But this method, the convergence rate of this method is also very slow, but it guarantees you that it takes you towards the root. So that is why this is available in literature, and generally this is known as the first method to find out the root of the function of single variable. This is a function of single variable. Let me write down the result for the 22nd iteration so that you can verify it whenever you do at home, and you can check either you are getting the same output or not. So after the 23rd iteration, the result is 2.3736. Okay, this will be the result you will be obtaining after performing 22nd iteration. And after one more iteration, if you perform, you will be getting the same result up to 4 decimal places. But whenever you increase the number of decimal places, you will see the difference in between these two results. But we are keeping all of calculation up to 4 decimal, so that's why you will be looking these two are same. So whenever we are at this level where we have the same result for 2 consecutive iterations, then you can take stop. Otherwise, you have to keep on doing new and more iterations, and unless we reach to a place where we have the same results up to 4 decimal places, till then we have to proceed. And with this, I hope you can do more questions at home for practice point of view and get a bit more hold in order to understand the method, how actually this proceeds. So with this, thank you very much and Assalamu alaikum.